Hello, um, this is my presentation on the application of supervised deep convolutional neural networks in the identification of palaeoenvironmental remains. In this presentation, I will first outline the most obvious problems of classification in archaeology, followed by the causes of misclassification. I've divided the causes of misclassification into two parts. The first part is familiar to all archaeologists as it deals with the incidental condition of the object in which it was found. The second involves the psychological analyst's specific causes. I will then briefly explain how convolutional neural networks work before moving on to the two case studies. I'm going to finish by discussing what I aim to do after the sheep and goat classification study. The most obvious issue with archaeological classification is the time and effort that is required. By automating archaeological classifications, we can begin to process larger samples in a shorter amount of time, releasing analysts to conduct more intellectually demanding tasks. By relying on analysts for classification, misclassification isn't only a possibility, but quite likely to be higher than in automated methods. The misclassifications are compounded by self-consistency, which Culverhouse et al. Estimated to be only 67 to 83% for experts without fieldwork experience, and 94 to 99% for those with fieldwork experience, although these figures are for only two dinoflagellate species. In the same study, the consistency across 8 individuals for the same two species was between 95 and 43%, but this dropped to between 83 and 86% for 23 species. Another argument I'm going to make is that because of the lack of time by experts, quality control and assessments are often overlooked in both academic and especially commercial archaeology. Because of these above problems, archaeology suffers a lot from lack of replicability and replication studies. It just isn't possible to replicate analyses that rely on classification by human analysts. These problems are evident in many aspects of archaeology. For instance, zooarchaeologists create different species assemblages when given the exact same assemblage. Human analysts vary in their use of sexing and aging methodologies, even when the instructions are formalized, and experience is a factor in basic tasks like sorting pieces of flint into raw material types. Of course, not everything is archaeologists' fault. A lot of the misidentifications are caused by circumstances outside of the analyst's control. It is impossible for archaeologists to completely ignore fragmented objects, for instance, although the population distributions between complete and fragmented objects should be similar given large enough samples. Taphonomic factors from before the burial to the storage of objects can all have an impact on the physical shape of an object. Then there are factors such as pathologies, age, sex, life histories, nutrition, etc. That can add their own flavor to classifying faunal remains. With pollen and soil micromorphology, visibility can be hindered when using a microscope, and this can also affect bones that have difficult to remove concretions. Measurement error can be a factor in cases where metric analyses are required for separating two classes. Homomorphism and heteromorphisms are also difficult for analysts. Homomorphisms refer to two different classes of objects resembling each other, while two heteromorphic objects, on the other hand, can look different but they belong to the same class. Uniqueness is yet another factor. How do you classify an object that has not been seen before? Do you give it its own class, or do you try to fit it into an existing one? Finally, different institutions and individuals utilize different reference materials, biasing analysts towards the shapes that they have seen. And I will talk about this in a bit. One of the bigger problems with relying on human analysts is that there are psychological causes of misclassification, which obviously shouldn't be present in any computer vision-based technique. Visual working memory is a particularly tricky part of human psyche to account for in analysis, since people's brains are wired in different ways. Human short-term visual memory varies between individuals from 1 to 5 objects, while the long-term memory capacity is generally large. With long-term memory, the recognition accuracy starts to suffer if there is a large variety of objects in a given category. When I say large variety, I'm referring to a paper by Conkle et al., who found that the accuracy dropped from 89% with just one example per category to 83% if there were 16 different examples in a category. And there is, of course, memory loss and false memories that have their own impact. While boredom is unlikely to affect researchers who have spent years training to become good at identifying certain objects, fatigue will nonetheless always be present in any task. Recency effect is related to memory, as it refers to the phenomenon of remembering the most recent objects or events best. This is important, for instance, for zooarchaeologists who go through an assemblage one by one. For instance, if you have 5 clearly identified bones that belong to, say, sheep, and then you encounter a similar bone that is actually a goat, but because of the similarity of the two species and the recency effect, your chances of misclassifying the bone is likely to go up. This is also why differential access to reference collections is an important but unaccounted factor in archaeological classifications. Another related effect is the positivity bias or expectation bias, which means that a researcher may have an idea of what the objects in an assemblage are going to be. An example of this might be a pottery specialist looking at an assemblage that was dated to Roman times. The expectation bias would be that no typically medieval pottery should be found. So while some of the incidental factors like fragmentation caused by taphonomy will always be there due to the nature of the data that archaeologists deal with, we should at least be able to get rid of the analyst-specific psychological factors by utilizing machine vision for our problem. My approach to object classification relies on images as data, although they can be bolstered by metric data. It's possible to use 3D data or videos as well. I'm going to delve a little deeper into deep learning convolutional neural networks in a bit, since they are the state of the art in machine vision. And before I go any further, I just want to mention that I'm using transfer learning, which means that I'm moving information from someone else's neural network into my own, which I then retrain with my data. This will allow me to get away with using smaller datasets and provide much faster training. What is the point of reinventing the wheel anyway? I have not used any data augmentation methods, but I will explore the possibility of doing so at a later date. So let's talk about how neural networks work. In general, the training of a neural network requires that original values are passed forward and the weights in neurons are modified in a backward pass. In a basic feed-forward neural network, the pixel values of an image are fed into the neural network. From the input layer, the pixel values are passed to the next layer, where weights and biases are added. The values pass through an activation function and then are passed to the next layer. In the final layer, the model outputs a prediction of which class the original image belongs to. The neural network becomes deeper if one adds more layers. Let's look at what happens in a single neuron in the first hidden layer. The pixels are vectorized for the input layer, from where all pixels are sent to the neurons in the following hidden layer. The neurons in hidden layers can be divided into a pre-activation and post-activation part. In the pre-activation phase, the pixel values are multiplied by an initially random weight. The values are summed and a bias value is added. This value is then passed to the post-activation part, where an activation function applies a nonlinearity to the value. This output value then becomes one of the input values for all neurons in the next layer, since all neurons do this. When we're training the model, we try to find the best possible weights by using a gradient descent algorithm. This is done by calculating the gradient of the weight and then making incremental improvements to it so that we find the minimum. Here, the red ball represents the weight, and the parabola is the derivative of the cost function, and each step towards the bottom is a slight adjustment of the weight based on the gradient. The model finds the best weights when the gradient is equal to 0. One of the first animation we saw the gradient descent as occurring in a two-dimensional space. The reality is that the derivative of the cost is actually much more complicated, and the gradient descent resembles more like a path down a hill. Descent is propagated backwards by using a backpropagation algorithm, which takes advantage of the chain rule of differentiation from calculus. The backpropagation is used for updating the weights in all neurons in all layers with respect to the cost of the model's predictions. In a convolutional neural network, we add at least one convolutional layer in which the inputs are mapped by kernels or filters, which are matrices of values that are applied to input feature maps, which are essentially just channels of the input image. These kernels stride across the image based on some predetermined stride, which is often every pixel as seen here, or they may skip some pixels. The convolutional neural network aims to learn the right set of weights in the filters, which will enable the network to find the most significant features that help the model to identify the subject. While individual filters may only show straight lines or curves, by training the weights of dozens of unique filters and combining them together, we can start to see increasingly complex features like eyes and noses. My primary case study concerns the classification of pollen grain types using convolutional neural networks with transfer learning. The motivation for automating pollen classification is the same as it is for zoo archaeological or other archaeological objects. It's time-consuming and subject to analyst error. A lot of early studies on automating palynology tried to hard-code the features of pollen grains into their algorithms, but these previous methods failed mainly because there are so many variables in pollen morphology. Considering factors like homomegathy, where the water content inside the grain effectively decides the morphological shape, it is extremely difficult to hard-code these features. Instead, using CNNs is better since they find the most pertinent features for you rather than having to spend a lot of time guessing what those features should be. The dataset I used is the Pollen 23E published by Concalves et al. In 2016, which consists of 23 classes and 35 images in each class. I chose this dataset because it was complex enough with its small size and varied classes. There is also a baseline study in which non-experts were asked to identify these grains based on training images. Another study by Sevillano and Asnate in 2018 claimed to have achieved a very high accuracy on this dataset with a relatively old convolutional neural network architecture called AlexNet. which itself was published in 2012 and has since been shown to perform worse than many other architectures on various machine vision benchmarks. My aim at first was to replicate what Sevillano and Asnate did, but with newer neural network architectures. I also only wanted to replicate the simplest method of theirs, since all of their three setups achieved essentially the same accuracy. So I went with just using transfer learning and softmax as a classifier, effectively replicating the setup B. Their reported accuracies for the three setups are around 96 and 97%. But as I looked at the confusion matrices and compared to my initial test results, I realized that they had calculated their accuracy and other test metrics incorrectly. These metrics should be possible to calculate from the confusion matrices, but the numbers derived from the confusion matrices do not match those reported. I have been in touch with the authors about this, but they did not provide an answer. My approach to this classification problem comes in two phases. The first phase was the pilot study phase, while the second phase still requires writing up. Both phases use Python 3, TensorFlow, transfer learning, and the same base neural network architectures, but otherwise the approaches are quite different. I chose Inception, ResNet, ResNet 50, and ResNet 152 as my base models because of their performance in the ILS VRC benchmark, all of which performed considerably better than AlexNet. The Inception and Inception ResNet models require image sizes of 299 by 299 pixels, while the two ResNet models require images to be scaled to 224 by 224 pixels. This scaling resulted in distortion in most of the images and may affect the results, although the impact is unlikely to be huge because the models would simply learn to identify distorted versions of the pollen grains. In other words, the resulting models would not be effective classifiers of non-distorted images. It's also worth mentioning here that ensemble models of all of these base models achieve even better accuracies in the ILS VRC benchmark. In the phase 1, I used TensorFlow 1 and Python 3. I divided the data using stratified tenfold cross-validation, where the final accuracy is the average accuracy based on each fold being used as a holdout fold, essentially covering the entire dataset. In this first phase, the weights in the base neural network were frozen, but the last fully connected layer and the classifying softmax layer were retrained because these two layers were originally trained to classify 1000 classes instead of the 23 in the Pollen 23E dataset. Since all CNNs require some hyperparameter selection, I first took the grid search approach, where I manually selected a set of batch sizes, a number of epochs, and learning rates. Even though grid search is quite unlikely to find the best weights, I chose it because it provides limits in which to conduct the analysis. Contrast this to manual search, which I chose as an auxiliary method to fine-tune the model performance. On the right, I've shown how grid search and manual search works. Manual selection is a semi-random process, and combining it with grid search allows me to focus on the most promising region of the hyperparameter space, as shown by grid search. I also decided to use Adam Optimizer as the backpropagation algorithm in manual search, whereas the grid search relied on stochastic gradient descent. For grid search, I conducted 240 10-fold cross-validation tests, which resulted in 2,400 individual models. On top of these, I did 62 additional 10-fold cross-validation tests in manual search, 36 of which were attempts to improve inception ResNet results, and all of the 36 failed to significantly improve the accuracy. The accuracies for all base networks are quite high, each best accuracy beating the accuracies I recalculated for Sevillano and Asnate's setups A and B, but not C. However, the manual search strategy for ResNet 50 model achieved better accuracy than the setup C, meaning my approach could be considered state-of-the-art for this particular dataset. The accuracies I'm discussing here are, of course, the averages of the tenfold cross-validation. As a comparison, here you can see the confusion matrix from the manual search strategy in my research on the left and Sevillano and Asnate's setup C confusion matrix on the right. The quantitative differences in each class come from the fact that Sevillano and Asnate did not include all specimens in their tenfold cross-validation, whereas all images were included in my research. I'm just highlighting here what I mean, these numbers. In phase 2, I've taken a different approach. I've gotten rid of the epochs as a hyperparameter, instead employing early stopping with maximum epochs. This means that the training process ends either after 5 epochs if the validation loss does not improve, or after a maximum of 100 epochs. I also used UCL's Myriad high-performance computer for the modeling, which resulted in massive time savings. When in the first study, I spent perhaps a month running all the models on my own PC. Now it took less than a day to create all the models. I only used grid search, but with more hyperparameters in terms of learning rates, so that I get a tighter grid. I added ResNet 101 into the mix as well. Another big change I made was the use of max voting ensemble modeling, as well as allowing for weights to be trained in all layers, not just the last fully connected layer and the softmax layer. In the second phase, I took 5 images at random from each of the classes for the holdout dataset and divided the rest of the data into tenfolds. The accuracies in this case are reported based on the holdout data and not as an average across the whole dataset, like in the phase 1. This approach allows a much better reproducibility than the phase 1 approach. Just to briefly explain the max voting ensemble modeling approach, it means that I first took a holdout set of 115 images, divided the rest of the data into 10 folds, used one of these folds as the validation set, then did that 10 times so that the validation fold was always different. This created 10 different models, the performance of which I could test against the holdout set. In the max voting ensemble method, each of the 10 models can vote which class is most likely for a given image, essentially giving me the power of 10 different classifiers. The human analog would be that there are 10 researchers who look at the same data and the most popular answer is selected. Phase 2 results are even better than the phase 1 results. I'm relatively certain that my training program of selecting hundreds of epochs in the phase 1 resulted in overfitting, which means that the model could not generalize to adequately classify the images in the testing fold. By decreasing the number of epochs by an order of magnitude in some cases, the models got rid of the overfitting and achieved much better accuracies much faster. Combine this effect with ensemble modeling and the accuracy reached quite easily above 95%, even up to 98%. This means that the best answerable model would only misclassify 2 images out of the 115 images. It is clear that convolutional neural networks are excellent classifiers of pollen grains, even when using small datasets, provided that one uses transfer learning. Ensemble modeling and newer neural network architectures will undoubtedly provide even better results. Analysts' time is likely to be better spent on trying to find ways of standardizing pollen shape for microscopy and photography rather than trying to find the most pertinent features on pollen grains like in the past. The next stage of my research is to apply convolutional neural networks to sheep and goat astragalite classification. Sheep and goat differentiation from their skeletal remains has long been a problem in archaeology, and being able to differentiate the two species would be beneficial because they occupy different environmental niches and thus require different management strategies, which will then tell us about, for example, human behavior in early agricultural societies and potentially about their social status. For instance, keeping goats is sometimes seen as something that the less well-off people do in modern societies. There are also differences in sheep and goat exploitation, with mainly milk coming from goats and wool from sheep. I chose the astragalus for this study because it survives in the archaeological record and it is relatively resistant to non-genetic variation such as nutrition. The current best method utilizes metric measurements and it could achieve 86.9% accuracy. So that'll act as the minimum baseline any new method should reach. The current best method uses the ratio of BPT and H measurements that I've indicated at the bottom right of the image. I've already completed the image retrieval phase, having taken photos of 100 sheep and 93 goat astragali from 6 different aspects. I've also centered the bones in the images and added a black mask around them to get rid of the noise. The next stage is to flip the images of bones that came from the right side of the animal so that all images can be considered to represent just the left side of the animal. This is done because most of the images are of the left side astragalus, but a significant proportion of the goat astragali are from the right side. So what will I do with this data? I will subject the images to the same CNNs and techniques as in phase 2 of the pollen study and create ensemble models. I'm relatively confident that this will produce good accuracies. Certainly above 90% should not be a problem. I'd be very surprised if the neural networks couldn't classify the images correctly. If the technique is successful, I will create a web interface for expert analysts where they can test their skills at identifying the bones from the same images and mark which part they found most useful in their identifications. Once I have the experts' regions of interest, I can compare those to the best neural networks gradient activation maps, similar to what was done on the right here. Particularly the GradCam technique. Finally, if there is time and I get further funding, I am considering taking further images of archaeological astragali that could be classified using zooms. This would allow a nice comparison of the accuracies between CNNs and zooms. Thank you for your time, and I look forward to your questions.